If you work in the electronics industry, you instantly connect the name Molex with, well, connectors. The Molex patented two-piece pin and socket connector design became an early electronic standard that is almost universally recognized as simply the Molex connector. So when we wanted to learn about advances in connectors for electric and autonomous vehicles, we naturally wanted to hear from Molex. With us today on Tech Chat is Matt McWhinney from Molex, where he is the Automotive Business Development Manager. Welcome, Matt.
Hi there.
So this is perhaps the most exciting time to be working in the field of automobiles since Henry Ford. I mean, the changes we're seeing are just rapid and revolutionary, aren't they?
Yes, it's. I liken it to the kind of the Wild West. There's so much of what we thought was normal is now changing, and new systems and new architectures.
Yeah, so absolutely. So with that, what are we going to be learning about from you today?
Well, today we're going to be talking about the design trends. We'll talk about some of the systems and a refresher on connectors, and then a summary and a look ahead of what we can expect down the road. And just to provide you with a little bit of background about who we are, you may not have heard of Molex. We are a connector company, and we are familiar to the automotive industry. A lot of the products that we've supplied have been on the harness and the header side of the business. But today we're going to talk about what is going on inside the modules, the interconnects that are connecting printed circuit boards together and elements to the printed circuit board.
Yeah, and I noticed in here that you have 5G under autonomy, and it's one of the things a lot of people are probably not aware of, that some of the coming advancements in 5G are going to be part of those future AV systems, particularly the ultra reliable low latency communication. So 5G is way more than smartphones and high-speed video download.
Yeah, it really gets down to high speed data and more data, higher speed, and higher dependency on the data.
Right. You know, as your next slide here indicates, we have and really become all too aware of the past year with the chip shortages that cars are transitioning from vehicles with electronics to they're really electronic systems that happen to move around.
Yeah, a lot of people. I mean, some of the new electronic or electric car companies think of them or sometimes refer to them as mobile computing systems. And the amount of electronic systems that are on vehicles continues to grow every year.
Yeah, those numbers are pretty astounding there that, you know, almost 50% of the cost of a car is going to be in the electronics pretty soon is really unbelievable.
That's a blended average too. If you think about that's a collection of the very high end, advanced, the luxury vehicles, along with entry level vehicles. So that, considering it's a blended average, that's a very astounding figure.
Oh, that's a great point because, yeah, some of the high end are then going to be significantly above 45%.
Yeah, and just to provide with a little additional perspective, when we talk about ADAS, which is ADAS is Advanced Drivers Assistance Systems, and it basically, in its mature full format, we can think of them as self-driving vehicles. But it's a lot of the safety systems. It's a heads-up display, it's high-speed computing, it's camera and lidar and radar. And then with EV, there are a number of main modules such as inverters, DC to DC converters, and battery monitoring systems and battery chargers.
Yeah, that's a good slide to follow up on the previous one, just showing how many different things are using a lot of electronics in these new cars.
Yeah, and each of these have their own microprocessor, and the microprocessor are connected to other systems such as the power board or communications board. So there's a lot of interoperability and connections that take place within even discrete modules like these.
So let's dive into one of those in particular. Let's look at ADAS a little more.
Sure. ADAS, if you think about what it really is in its most simple format, ADAS is really a high-speed data collection and processing, and then forward the results of the data onto something else, whether it's a high-speed computer, whether it's a display system, whether it's a safety system that will tell the vehicle to slow down or to move to the left. And it is really that from the lowest common denominator, like printed circuit boards and microprocessors.
I see that term here. You got telematics. I get it seen used more often in the autonomous vehicle industry, and I tend to think of that as broadly as you're kind of using telecommunications and data and the information processing to improve vehicle and/or fleet performance. Is that close enough?
It is, but it also can involve coordinating geographic information and tagging it to where the vehicle is. And then telematics can be real time updates with something that's particularly unique, such as maybe a crash or vehicle circumstances that are around the vehicle. So we hear vehicle to vehicle, vehicle to the grid. And telematics can be a system that allows the external to communicate with the internal of the vehicle.
That's very helpful because I'd been seeing that term and hadn't seen it really detailed very well. So if autonomous vehicles are kind of 1A on the list of driving advances, then EV has to be 1B.
Yeah, exactly. And if you think about it, we've gone from a mode where we had a battery, and then batteries have increased in voltages, and multiple batteries have been added. We've moved to hybrid types of vehicles where it's a battery assist, all the way to full EV, where the battery systems are literally driving and powering the vehicle. It is the battery bank is the gas tank, and that requires a lot of additional systems that are involved with the charging, the conversion of from AC to DC and DC to AC, and converting to different levels of DC. That we call those DC to DC converters. But each of those are unique functions and have become very critical for the performance of EVs.
Yeah, and the key consideration here of increasing the connector innovation to reduce failure modes. Your note there, I know that just about any scale you look at, it's those connection points that are the highest risk of failure. Whether we're talking about the chips connecting to a printed circuit board, or connecting PCBs inside a system, or connecting my USB charging cable to my phone, those connection points are really high failure risk items.
Yeah, exactly. If you think about it, this is what the automotive industry has become very good at, is to make sure that they do their homework up front and do failure analysis. So that part, that chip or that connector needs to survive hundreds of thousands of miles with lots of shock and vibration over multiple temperature changes from minus 40 up to and over 100 degrees Celsius. And that's difficult. The designers of a lot of consumer electronics don't necessarily plan on that when they're designing handheld cell phones and so on.
Yeah, that's exactly right. I mean, just the picture you have here, the plug-in, that can get wet, it can get dust, it can get oil. I mean, all sorts of nasty stuff on it, and it still has to work reliably.
Absolutely. This slide just accentuates or punctuates what we just mentioned moments ago, is that vehicle electronics need to survive some pretty demanding circumstances and conditions that fortunately the automotive engineering society and engineers have realized this, and there are a lot of requirements and targets, performance targets, that any electronics in vehicles have to hit in order for them to be placed in any modern electronics, automotive electronics.
Yeah, now that you have the ease of assembly there, and mentioned the if I'm pronouncing this right, poka-yoke, and so that's that concept developed in Japan under the Toyota production system, right?
Yes, it is, and it basically means, in very crude terms, making it stupid-proof, so that somebody can't put a connector in backwards or put the wrong connector into the wrong receptacle. So there can be keying that takes place within connector systems.
Very good. Well, I certainly need things that are stupid-proof quite often. So electronics in these automotive systems are drawing from many of the technologies and concepts we see and use in our homes and office, aren't they?
Absolutely. And I would take it one step further in a lot of consumer devices like mobile phones and handheld computers and earbuds and whatnot, because they are pushing the limit in terms of higher screen resolution, touch screen, higher densities, higher performance, and software defined architectures. And that's the direction that automotive is also going.
Yeah, obviously we get used to having these things with us all the time, and now, like shown here, touch screens and lots of data and information. Just we've come to expect it, really.
Exactly. And the challenge is how does an automotive engineer take advantage of this technology and yet still build in the reliability that's needed for electronics to perform reliably on a vehicle for many years?
Right, because as you mentioned, this is a much more difficult environment. And then that key phrase you just said of many years, I really don't want to be replacing my car every 18 months like I do when I drop my smartphone.
Exactly.
So you mentioned, you're kind of talking about the top-down application space for this hardware. And so with that, now let's dive into some of the low-level hardware.
Yeah, I thought what we could do is just have a little bit of a refresher and talk about some of the interconnect technologies. And this is familiar territory for people that work in these systems, but there's wire to board, which is just what it looks like. And then there are two that I'm going to highlight today: FPC, FFC connectors, and also board to board connectors.
Yeah, and one of the things you can kind of see with this image is not just that there is a wide variety of connectors, but in all of these, really miniaturization is a big thing here. Everything's getting smaller, but you're also packing more lines, more signals into each of these smaller cables and connectors.
Yeah. More signals, more lines, and at higher speeds or higher frequencies as well.
Right, yeah. So let's look at the first of those, the FFC.
Sure, the FFC, and we sometimes say the same. We say FFC, FPC, flat flexible cable, or flexible printed circuit, but these are typically a single connector element that connects a ribbon type of a cable. And there's multiple form factors, there's different orientations, there's different locking systems. And in the consumer world, consumer electronics, they've been getting very small. I would even say for automotive, they may be even a little too small for the assembly process. But nevertheless, it allows for high density connecting, say, display systems to control modules for the big displays that we see on vehicles, or connecting two printed circuit boards together. That's the best way that an engineer can figure out how to connect them.
Yeah, I can remember having an e-reader years ago that quit working, and I took it apart and found that the FFC connector like this that you show here had kind of come loose. The cable had come loose, and so put it back together. But the fact that a benign environment like that it failed kind of gives me a feel for the challenge of doing this in an automotive environment.
Exactly. And in circumstances like that, with that concern, then they would search for a connector option that has a locking system that will hold it in place for the automotive application.
So a lot more engineering effort goes into the design and the material selection and the testing of these connectors for the automotive markets than would be necessary for a commercial. And so these FPC connectors look and function completely different from the other one you mentioned, board-to-board connectors.
Yeah, and a board-to-board connector, it's a two-part design with a receptacle that's typically soldered to a printed circuit board, and then there's a plug which could be either soldered to a printed circuit board or to an FPC cable. They tend to be very high-dense connectors. They have a lot of different areas of design freedom, such as having power endpoints. They can be very small, but they are also used in some automotive applications when very tight spaces are needed to make a connection to a printed circuit board.
So what are the key challenges in these board-to-board connections? Is it the physical stress during the mating process? Is it the vibration in automotive, temperature cycling, something else, all the above?
All the above, to be very honest. And you hit on some key challenges that engineers like those at Molex, that we have been innovating and designing our board-to-board connectors so that they, when they mate, they don't break if they're somewhat misapplied. And there's also floating systems that where the board to boards, they will literally float. They can move within a certain degree of freedom from the X and the Y and the Z footprint. And what this shows is just some of the variations of things that when engineers are designing these, and things that they take in consideration. What's the spacing between the pins? How tall are they? Is there power requirements? If they're floating, how much do they need to move? How are they assembled? What are the requirements? And the same things can also exist, same aspects for FPC, but I just happen to feature this because these are very unique and interesting connectors.
Yeah. And to one of your earlier points, this is probably a big reason why Molex works so closely with your customers, or at least with one of your bullets. And because you can help know what questions like this need to be asked, like how much float is needed, and then guide us to the best solution.
Sure, exactly. And that's a good lead into the next slide, discussing floating board to boards. Just to provide some visualization, these connectors can literally move from an X and a Y and a Z and angular. That means that either through the assembly process or tolerance stacking, or the most fundamental need is they can reduce stress on the solder joints from shock and vibration and temperature fluctuations as the vehicle goes through its life cycle.
Yeah, I know that allowing the components to move relative to one another and still maintaining electrical connectivity is got to be really difficult, especially at high frequency.
Yes, and I don't know how the engineers come up with these ideas, but it definitely is evolutionary. It's one idea is stacked on top of another idea.
Yeah, pretty incredible. So, Matt, you've introduced several key considerations in the connector selection, but what are a few other connector characteristics that system designers should be looking for?
Yeah, this is just kind of a summary of what good automotive connectors are going to, they may incorporate one or more of these products that have float, or they may need to support a high enough level of data, or they may need to have a dual contact where literally if one of the contacts, there's an intermittency, there's a backup connector. How easy is it to assemble? Is there locking? And can the connector system incorporate sealing? But a lot of these, because they're inside the module, we don't necessarily have to worry about seal because the entire module is sealed.
So, with that educational background you've given us, now let's start looking at the actual applications.
Yeah, and I'm just going to talk about some of the systems that these interconnect technologies are used. And these are all internal connector systems within ADAS and EV. EV battery packs are key components for electric vehicles. And one aspect, design aspect, that a lot of attention is being applied is for sensing line circuits on the battery packs. How are those battery packs being monitored all the way down to an individual cell level? And there's been a lot of innovation, wire to board, which has evolved to printed circuit board technology, which is now evolving to flat flexible cable to simplify the manufacturing process and lightweight. And all of those interconnects need a connector on the end. So Molex has been working on connector systems that allow these sensing circuits to be connected to battery monitoring systems. Another key aspect for electric vehicle is the power control in modules such as DC to DC converters, inverters, and chargers, as well as motor controllers. And what's been happening is they have evolved to multiple board systems. Sometimes they're even combining, engineers are combining DC to DC converters and chargers together in the battery pack. So there is a collection of printed circuit boards, and then they in turn need to communicate with each other. And that's where having sense line or sensing connectors that are capable of surviving the shock and vibration. Also, there can be some higher voltages, not just the 12 volts or even lower voltage. These can be 48, 100 volts, or even higher.
Yeah, that exploded view just kind of gives you a real feel for not only the complexity of the electronics, but the complexity of the physical assembly of what is just a single module in a system.
Yeah, and those are blind mate connections, which are either made by hand or automation. So the precision and having a little bit of float in those connectors is really makes the difference in their on how well they perform.
I would imagine.
And this slide, we're getting into some very specific, some design features that may be of value to an engineer as they're looking at how do I make these parts go together. For instance, do the connector systems have dual contacts so that there are high reliability? Are they rated at the temperatures? Will they be able to be properly mated with a poka yoke or the assembly process? So all of these design considerations need to be taken and factored up when making connector selection choices.
And your first bullet there is just a reminder of how difficult these challenges are because the voltages are going up, but everything wants to be closer together, which means your dielectrics have to be stronger. And then more dielectric means more capacitance, and therefore it's harder to do high frequency. So these are really difficult engineering challenges that you guys are going after.
Absolutely, well said. So we're going to talk a little bit about some of the ADAS systems and some things that engineers may want to take into consideration as they're looking at these. LiDAR and radar are two systems that are used for obstacle detection and collision and accident avoidance. And like the previous systems, there are often multiple printed circuit boards, there's high frequencies, and these can be placed in areas of the vehicle that see lots of shock and vibration and temperature extremes. So the need to have rugged and reliable interconnect technologies that will allow these printed circuit boards to be densely packed and economically packaged is a challenge that engineers have to go through when they're making their design choices.
Yeah, and this is where, some of those automotive standards, become so important because this can be part of what is really a very critical function if it's giving data to the system to decide where to drive, where to stop. So very critical.
Yeah, exactly. And determining, is that obstacle in front of us, is that a tree or is it another car or is it a child on a bicycle? And that's what these systems can help with, either the driver or in advanced systems, high speed computers, to make choices and create alerts and take corrective actions.
Yeah, it's a lot of data moving very quickly and it needs to be reliable.
Yep. And getting into a little bit more specific, with the interconnects, they need to be rated at fairly high temperatures, even if they're outside of the vehicle. With this last summer and seeing some of the warm temperatures either in or outside of the vehicles, it has not become uncommon for them to see up to 100 degrees Celsius has been happening. And then the amount of vibration. So designers have been turning to consumer connector technologies, but unless if they are automotive rated, they have to be really careful about making those choices. So it is essential that connector systems have been thoroughly tested and vetted for the level of performance that's needed for the application.
Do you think that over time, the advancements that you guys do in making high reliability versions of these will then push back down into those consumer applications as well?
Absolutely. It is a circle that proceeds that way. So I think for the longest time, the consumer industry was probably ahead in terms of the innovation, but now we're seeing the need for reliability circling back or feeding back into the consumer with connector systems that can survive drops and extreme temperature ratings. And that will ultimately be good for the entire industry. In this slide, what we are talking about is camera systems. And you may have noticed an increase of cameras, and sometimes they're not even completely visible. But camera systems have been first used in the backup cameras, but now they're forward facing cameras. There's cameras that, in some instances, are mounted on the mirrors, or someday maybe to replace the mirrors. Also, for the ADAS systems, vision systems that can track and determine and ascertain what obstacles are around the vehicle. And the goals or the challenges of these is how to package them, how to assemble them. Are they sufficiently robust for the application? And do they have the required or the needed resolution for the application, such as determining, is that a tree or is it a child on a bicycle?
Yeah, and that goes back to the earlier slide about how much electronics are going into these systems. They're talking about high-end automobiles having, like you said, multiple cameras looking out front, some out the back, to the side, and processing data from all around the car.
And the way with cameras, a lot of them have been standalone cameras. So they are, and that aids in the miniaturization and the assembly. Often they can have a single coax connector that provides both signal and power. Inside of these systems, there can be some pretty interesting and sophisticated connector technologies that allow the printed circuit board with the microprocessor to float on that coax connector stack inside of the sealed environment. And we sometimes call those camera backshell connectors, but that's one class of connectors that are used on standalone cameras.
Interesting. Those connectors look a lot different than some of the other ones we've been looking at today.
Absolutely. It is a little different. It's an internal, external connector system, but it has evolved in order to help miniaturize and improve the reliability, to take the stress off the solder joints at where the connector meets the printed circuit board.
That makes sense.
Yeah, and the other type of camera system is an integrated camera, that where the camera is integrated into a module that has some other things going on, or cameras that have multiple printed circuit boards in them. So with these, there are other connector systems that are not the previous, but they're more traditional. They could be FFC, FPC connectors, or floating board to boards. And it just really depends on how much space and packaging exists to allow them to fit the camera to the printed circuit board, and is the connector system rated at the sufficient frequency response.
Yeah, there's not a one size fits all. And even thinking about the automobile application, you're going to need a lot more data looking out the front of your car because you're moving in that direction. You got to process it quickly. Out the back, you might want to know what's behind you, but it's just not that critical.
Sure. And there's also cameras inside the vehicle too to determine if there's occupants. And let's think about commercial vehicles. Is the driver maybe getting tired and nodding off? And that actually is a concern with people that are driving, for instance, delivery vehicles.
Oh, that's an interesting point.
Another extension of that, just as there have been there's been attention to how to connect cameras to printed circuit boards. Well, think about the displays, those ever increasingly large displays that are now have become touch centric. They need to be connected to one or more printed circuit boards. So that requires a high reliability connector system that can survive the shock and the vibration with enough pin counts, enough frequency resolution. So those are all design needs and goals that engineers take into consideration when they are designing and integrating displays into dashboards and into navigation systems.
And I would imagine you'd have to be part of that design discussion for how you're going to do maintenance on these things. When they fail, the connectors, some of them have to come apart so that they can be replaced components.
Absolutely. And these connector systems, like you say, the serviceability in the event that a display may need to be serviced, having a connector system that can be actuated and without having to use special tools or without having to destroy printed circuit boards, a connector system that allows the display to be easily enough replaced.
Easily enough. That's a
Yeah.
So what you're saying is it's still not going to be cheap for get my car fixed.
Depends on who's doing it.
Well, that's great. So why don't you just kind of pull everything together for us here as we run out of time?
Happy to do that. And I think the easiest way to say what we can expect to see is more connector systems, higher speed, higher density, more high speed computing, the need to interconnect more components to more circuit boards, and having connectors that are high reliable and with locking systems that were designed from the ground up to be automotive connectors. And that's kind of the design challenge here: is how can the connector industry catch up and be a source of design inspiration to the ever innovative automotive designers that are working on next generation vehicles.
So considering the name Molex has been synonymous with connectors for about 70 years, it's really not too surprising that they're still leading innovators in this space. So Matt, thank you very much for joining us on Tech Chat today and giving us an education on connector solutions for automotive applications. I know that I found it helpful, and I would imagine that our viewers will too.
Thank you very much, Dale. And on behalf of Molex and Mauser, I was happy to take these few moments with you today.
Excellent. Thank you so much.